All right, now we're going to do an example in Excel for a decision with multiple objectives where we're using the normalization and marginal rate of substitution approach to derive the weights. In our case, this is selecting an apartment to live in. We're going to have 5 alternative apartments to compare across 6 metrics. And you can download an Excel file with the data as a template at tinyurl.com/apartment decision. I encourage you when you go there to download it as an Excel file and open it in Excel instead of using it in Google Sheets. That's tinyurl.com/apartment decision. All right, here we are in Excel, and you're going to notice a few things here. These first 3 rows up here start off with our overall objective. Live in an affordable, comfortable, and convenient apartment. That is broken down into several sub-objectives: decreasing cost, increasing our space, increasing ease of business travel. A couple related to the commute, one about improving sustainability, one's about decreasing the commute time. And finally, we want to live in a hip neighborhood. The row below this here has our metrics. Each one is linked to an objective. The rent for the cost, the square footage for the space, our increasing ease of business travel. We'd like to minimize the time to the airport in minutes. Increasing sustainability of the commute, we want to minimize the miles to the subway. Decreasing commute time is decreasing daily commute time in minutes. And living in a hip neighborhood, we want the lowest percentage of people over 65 living there, so it's not a retirement community as we move into an apartment after graduating college. All right, you're also going to see we have 5 different apartments listed over here in the rows 5 through 9, and each one of those has their rent entered, their square footage, the number of minutes to the airport, et cetera, et cetera. We've collected the data to evaluate each one of these alternatives. Now I'm going to go ahead and select these first 3 rows and right click and hide them just to get a little more real estate on the screen. All right, to set up some of our later calculations, we're going to compute a few things about each metric. We want to know, is more or less better for it? And then we want to know what the best value is and the worst value is for each metric. And then finally, we want to know the absolute value of the range of that metric. And so with rent, less is better. So put a 0 in. For square footage, we want a big apartment. So bigger is better. Time to airport, less is better. Miles to the subway station, less is better. Daily commute time, less is better. And as we've set it up here, we want fewer percentage of people over 65 living in the neighborhood. With that information, we can enter in equations for what the best and the worst rent, square footage, time to airport, et cetera, is for each different metric. In this case, you'll see, I'm just going to say equals if more is better equals 1. So if more is better, the best value is just the maximum of these values. And if more is not better, then it's the minimum of these values in cells C5 through C9. Can hit return there, and we see it's $800 is the best one. For worst, enter a very similar equation, equals if more is better equals 1. So if more is better, then the worst value is the minimum value. But if more is not better, then the worst value is the maximum value. So now we can see that the worst value is the highest value for rent. Finally, for the range, in this case, we want the absolute value of the range, so we can just put in equals ABS, which is the function for absolute value, and just say best minus worst, and hit go. Now with these 3 cells, I'm going to hit copy and highlight all of my cells over here in this range, and I'm going to want to copy formulas and paste the formulas. Just to go through the long way of doing that. There we go. And we can also get all of that centered in our cells. So let's just see if that worked. For square footage, the best one is 1,500. Yeah, the biggest apartment, and the worst one is 500, and the range is 1,000. Let's come to commute time. The best one is the shortest, so that's 12 minutes. Yep, that worked. And 30 minutes is the worst, and the range is indeed 18. Great. So now we're going to go back to our slides and check in about how we're going to actually normalize our values. All right, you might remember from another video this slide about college rankings. Let's check it out. And what it says here is ultimately when we're normalizing, we are simply saying the worst value should get a score of 0 and the best value should get a score of 1. Here is the general formula for that. So your actual value minus the worst value divided by the best minus the worst. We're just going to go back to Excel and apply this formula to get normalized values for each metric for each alternative. All right, so what I want to do is write a formula in this cell, cell C17, and I can just copy and paste to every other cell and have it work. So I'll put in the equal sign to start my formula. And I want it to equals the actual value for this top alternative, which is East Falls Church, and for its rent. And I want to subtract the worst value for rent. And then I want to divide that by the best minus the worst. Now this formula right here, I can hit enter and it works great for this one cell. But in order to get it to work for all other cells, I'm going to need to put in some dollar signs to make sure that it always stays referring to rows 12 and 13, because these are the two rows that have our best and our worst in them. So coming back here, edit our formula. And I want to make sure I'm going to use the shortcut on Windows, which is F4. On a Mac, it's flower T, and it cycles through the different options for where the dollar signs are that lock in your absolute references. We want our rows to be solid and our columns to be able to change as we copy and paste. Something else we also want to do is go ahead and get the formatting correct for this. So I'm going to reduce our number of significant digits there, or digits after the decimal point, and it's centered. I like that. Now all I need to do is select all of the cells for all of my alternatives, and you can hit Control D and Control R, and it'll copy that formula across to all of those cells if we've written it correctly. Let's check it out. Let's go to time to airport just as an example. And scroll down so you can see all the data for it. It says our highest normalized value is 1, so that should be our shortest commute time, and indeed it is. Our lowest is with the Elms, so that should be our longest commute time, and it is. And then it is interpolated linearly in between those. We can do the same for square footage, where our best one is our biggest at 1,500. Our worst one is courthouse, which is the smallest at 500. And take one of these that has a normalized value of 0.5. It should be halfway between 500 and 1,500, which is 1,000. And indeed it is. So it looks like our formula is working well. Now we're going to scroll down and start thinking about how are we going to calculate the weights for this decision. So given that we know that these marginal rates are really what are modeling our willingness to trade off one metric for another metric, we're going to start with the marginal rates. And we're just going to show you how to do this in Excel. So we're just starting with having those marginal rates given to us. For instance, someone would trade a minute reduction in commute time, so that's like 1 better in commute time, for 1 minute worse going to the airport, or a minute reduction in commute time for $20 additional in monthly rent cost. Now, where do these numbers come from? How do you get them? That's a whole nother video, a whole nother topic. And I think the bottom line on that is these numbers are not precise. Depending on the context, you ask someone what these are, or if you have a group who's responding, marginal rates are not crisp, derivable value statements, which gives all the more reason for us to do a solid sensitivity analysis after we develop the scores for our alternatives. Now, so we have these marginal rates. How do we get to weights? And from the prior video, you might remember that we developed this equation where the marginal rate of metric X to metric Y, so let's say dollars per square foot, equals the range of dollars divided by the range for square feet multiplied by the weight ratio of those two things flipped. We can solve this for the weight ratio, which would be really what we want to get, just by multiplying both sides by range of y over range of x. And this is the formula we're going to use in our Excel sheet. And in fact, we're going to use it in the following way. Because all of our marginal rates are per 1 minute of commute time, we're going to say the weight for any metric divided by the weight for commute time equals the range of that metric over the range for commute time times, and this is where it's going to be a little bit, it says marginal rate of x over y. What we actually have, we don't have the marginal rate of commute time per each metric. We have the marginal rate of each metric per 1 minute of commute time. So what this turns out to be is 1 over the marginal rate of substitution for y over commute. So how many dollars per minute of commute, how many square feet per minute commute, etc. Now all we need to do is go back into Excel, take this equation, and you can see why we calculated the ranges earlier, and enter it in, and this should calculate our weight ratios, which is what we're going to start with on path to calculating the weights themselves. All right, so back in Excel, this first row is how many of each metric are we willing to trade off per 1 minute of commute time reduction. And it was on the slides, you may not remember it, it was $20. It was 10 square feet was the equivalent of 1 minute of commute reduction. It was 1 minute of time to the airport. It was half a mile to the subway. Now, daily commute time per 1 minute of daily commute time is by definition 1. And then 1% change in persons over 65 would be the equivalent of a 1 minute reduction in commute time. So these are our marginal rates in row 24. This next row is where we compute the weight ratios. And we talked about what that equation is going to be. And I'm going to start entering it here using the ranges that we entered earlier. So we're going to need to have, what we want to get is the weight of rent per the weight of commute. So that's going to be the range of rent divided by the range of commute. And we actually always want to be dividing by the range of commute. So I'm going to make that $G $14. And then we're going to multiply that by 1 over the marginal rate of dollars per 1 minute of commute time. That answer is 2.9 is the weight for rent is 2.9 times bigger than the weight for commute time. And we can copy this formula across by selecting those cells and hitting Control R. So we've got the weight ratios of each metric relative to the weight of commute. And now what we need to do is figure out how to compute the weight itself for each metric, not the ratio of it to the weight of commute. And we're going to go back to our PowerPoint slides to set up that process. Hey, I've got some good news, which is that there's an easy way to calculate the weights once you have the weight ratios. And that's just to sum up all the weight ratios and divide each individual weight ratio by the sum of all of the weight ratios. But you may be wondering why we do that. Well, I want you to remember that each one of the weight ratios represents an equation. And for instance, the weight of rent divided by the weight of commute time equals 2.9. One of those equations is not that useful because it's the weight of commute time divided by the weight of commute time equals 1. So that's not really a useful equation. So we end up with 5 equations of those weight ratios and 6 unknowns, the 6 weights. Our 6th equation is just that all the weights sum to 1. And that's just a convention that is used. How does that look? If we were to set this up in terms of a matrix, you can see the weights for each of our 6 metrics. And here you can see the 6 equations. The first one is that if you sum up all of the weights, it equals 1. The next equation is just the equation you get from the first weight ratio, that the weight of dollars per the weight of commute time equals 2.9. So that means the weight of dollars minus 2.9 times the weight of commute equals 0. So here's our set of linear equations. You can solve this by substitution if you have time, or you probably have other methods that you know to solve this. The bottom line is this is why it works, but you don't need to remember all of the linear algebra. You can just divide each weight ratio by the sum of all of the weight ratios. All right, now we're back in Excel, and I'm going to enter the equation we just talked about, which is simply I want to take this weight ratio and divide it by the sum of all of the weight ratios. Now I need that sum to be an absolute reference to those cells, so I put the dollar signs in front of all the cells and hit return, and it says, okay, I'm just gonna add a parentheses for you. Now I'd like to kind of clean up a little bit of the extra decimal places so it looks a little bit nicer. And now I can select all these cells and hit Control R, and it'll fill this formula from left to right. Here are all of our weights, and just to check, you can sum these up and see that indeed they do sum to 1. All right, booyah, we've got our weights right here in row 26. We've got our normalized values up in the table above. And now what we need to do is multiply out each normalized value by the weights. Make sure we're using our relative and absolute references correctly, and so that we can copy and paste this formula throughout the whole matrix. Now there are some other formulas you can use, like sum product, that would do all this without having to make this intermediary matrix. But I kind of like it. It lets us see what's happening, and lets us make some good graphs later if we want to. We're not using sum product here. We're just going to use sum. So now we just want to sum up the totals for each of the different metrics for East Falls Church. And that's its score, and I'll copy that down. And we want to look at the rank of each of our alternatives. We'll just say rank, select on the score, comma, and then select all of the scores we want to rank it against, and hit F4 to make that an absolute reference. And we can copy and paste that down. Clean up a little bit of the numbers so that they're what we want to see. And we're good to go. This table is now all finished. It's operational. We can see that Annandale is the top choice and East Falls Church is the second, and we could dig in to figure out why. And anywhere along the way here, for instance, if we came back and we learned that, we actually want to see what happens if we change some of the marginal rates. Like what if we found out that, time to airport in minutes just really isn't that important. So they're actually willing to give 10 minutes of airport time for every 1 minute of commute reduction, because maybe they only travel to the airport once every 2 weeks and they commute, 10 times every 2 weeks. So you can put that in, you see the scores automatically update. Both the scores and rankings changed, but the top 2 remain the same. And that's going to be what sensitivity analysis is all about, is how do you look at changes in your marginal rates and see if what it takes for certain alternatives to be the top ranked or to become the top ranked, or even if it's possible for some to be top ranked. All right, that's it. Have fun with the spreadsheet.